Check. Okay, let's get started with today's interactive session on fluid and particle mechanics. I am your teaching assistant Shankar, and this course is offered on NPTEL by Professor Sumesh and Professor Madhivala Basavaraj. We will meet every Mondays from 6 o'clock to 8 o'clock to discuss any questions, the previous week's assignments, and any new topics that are numericals related to topics that have been discussed in class. Let's get started with week 3 assignments. So in this week, we'll do 2 weeks worth of solved assignment or unsolved assignments from week 3 and week 4, since the dates of submission of the assignments are already over. So week 3 assignments were actually scheduled to submit sometime in 16th of August, and week 4 assignments were supposed to be submitted on 23rd of August. So with that, we'll get started with the questions on week 3 assignments, which are dealing with two-dimensional Navier-Stokes equation. So let's read the question. For a developed laminar flow in a two-dimensional channel of gap 2h, flow between two parallel plates separated by a distance of 2h, driven by a pressure gradient. Write the following. In all questions, y is measured from the top one. So let's consider a fully developed laminar flow in a two-dimensional channel of gap 2h. So let's consider that this is 2h, and since it's a pressure driven flow, we have already solved this equation for ur, which will come out to be in fact parabolic, such as this. Now let's see what the question is. The first question refers to the distance from the top wall at which the velocity vanishes. Now the question is u is equal to 0 when y is equal to question mark, and this is very easy question, and we know that this statement comes from the boundary condition for the solution, which is the no slip boundary condition, which is given as u is equal to 0 at y is equal to 0. Therefore, the answer is y equal to 0 times h, or equal to 0. And we know that velocity is 0 at the walls. Okay, let's move on to question number 2. Same starting paragraph. For a fully developed laminar flow in a two-dimensional channel of gap 2h, flow between two parallel plates separated by a distance of 2h driven by a pressure gradient. The distance from the top wall at which velocity equals the maximum velocity is y is equal to question mark. Can anyone give the answer over here? I'll wait for a couple of minutes, see if you're able to get this on your own. Okay, as we said, we have 2 walls, and we know that the maximum velocity happens when there is du by dy is equal to 0. This can be maximum or minimum. And in the class, we have seen that this maximum has occurred at uh, y is equal to uh, actually the midpoint. Since this distance is 2h, this is y is equal to 0. Therefore, this distance is equal to h. Therefore, uh, u max occurs at y is equal to h. Now, there is one more case in this question where the velocity vanishes. This is at y is equal to 2 times h, uh, u is equal to 0. And at y is equal to 0 and y is equal to 2h, uh, we'll be given the u is equal to 0. We'll get u equal to 0. So similarly, you'll get the maximum velocity of the flow at the center of the line. This is very proved in class, and the center of the line here is given by y is equal to h. We'll move on to the next question. For a fully developed laminar flow, again same part of the starting paragraph remains the same. The distance from the top wall at which the velocity equals the average velocity. Now, this is a little bit tricky question. Can anyone think of the answer? I'll just wait for a couple of minutes. So we know that the average velocity is 2 by 3 times the maximum velocity. This was very much discussed in class, and you know that the average velocity is uh, given by the average velocity is given by the maximum velocity uh, times 1 minus y by h, and this is 2 by 3 u max. Therefore, from here y will get this as h by, sorry, you'll get y is equal to you'll get y is equal to h by 3. This is 0.33 times h. So this is the correct answer for this question. Moving on to next question. The calculation of velocity profile on a flat plate. This is a flat plate question. Is an important problem in fluid mechanics. As useful approximation for the x component of velocity in an incompressible laminar boundary layer is parabolic variation from u is equal to 0 at the surface of the wall to the free stream velocity, free stream or approaching the fluid with uniform velocity u at the edge of the boundary layer y is equal to delta. The equation for the velocity profile is u by u is equal to 2y by delta minus y by delta the whole square, where delta is a function of x and k is a constant, and delta is given by k times root x, square root of x. Can be shown that the simplest expression for the y component of velocity is this is actually not u, and I would like to write this as v. So let's just stick to this notation right now. So it is shown that v by u should be equal to delta by x power a times b into y by delta the whole square minus c into y by delta the whole cube. We need to find out what the values of a, b, and c are. So how do we solve this question? We have the value of u as a function of uh, x comma y, where u is equal to 2y by k into x raised to 1 by 2. We know that delta is equal to k x power 1 by 2 minus y square by k square times x, because delta square would come to k square times x. What we need to do is find, since it is since it is given that it is in an incompressible laminar boundary layer, we can directly use the equation of continuity to find the velocity profile. So we can write dou u by dou x plus dou v by dou y should be equal to 0. From here we know what is u as a function of x. We just need to differentiate dou u by dou x and find dou v by dou y as a function of y, and then integrate that function f of y to get the equation as in terms of, or equation for v. So I'll just give a couple of minutes to for everyone to finish off or find the answer in this case. Then I'll start my answer. Okay, let's get started with the solution. We know that u is 2y by k x raised to 1 by 2 minus y square by x square. Let's start by finding out what is dou u by dou x, which refers to dou by dou x of 2y by k x power 1 by 2 minus y square by k square x. So when I differentiate this, we can rewrite this as dou by dou x of 2y by 2y by k x raised to minus 1 by 2 minus y square by k square x raised to minus 1. Therefore, when I differentiate the first term, I'll get differential of x raised to n is equal to n x raised to n minus 1 dy dx. Based on this, I can write down the first term as minus y x raised to minus 3 by 2 by k minus uh, y square by k square x raised to minus 2. This would become in fact plus over here. Therefore, we'll find dou u by dou x to be equal to y square by k square x square minus y by k x raised to 3 by 2. And what we need to do is to find dou v by dou y, which is minus dou u by dou x. Again, this equation of continuity is in two-dimensional because just because it is a flat plate, the z-axis doesn't matter in this direction. Only the u and v just matters here. So we can write dou v by dou y as minus dou u by dou x from continuity equation. Therefore, let's write what is dou v by dou y, which is negative of this term, which is y by k x raised to 3 by 2 minus y square by k square times x square. So let's try to simplify this, or let's try to integrate this. So v can be found out by integrating y by kx raised to 3 by 2 minus y square by k square x square dy. So integrating of integral of y dy, integral of y raised y dy or y power n dy would be the result y raised to n plus 1 by n plus 1. So let's do integral of y dy would be y square by 2k x raised to 3 by 2 minus y cube by 3k square x raised to 2. Yeah, that's exactly what we have gotten for y. Obviously, there will be a function of x which we, for our purposes, we are in fact neglecting it. So we have gotten an equation for just yeah. So we have got an equation for y in v in terms of y. Now let's try to bring it in the form that was asked in the question as delta by x power 8 times by delta the whole square minus cy by delta the whole cube. So let's try to simplify this equation by bringing back delta as k times x raised to 1 by 2. So v is equal to y square by 2 times, you know that from here if I take kx raised to 1 by 2, I'll be getting delta times x, because x raised to 1 by 2, x raised to 3 by 2 can be written as x raised to 1 by 2 times x. So kx raised to 1 by 2 can be clubbed together to write delta, and the other part would be y cube by 3. Again, k square times x, as we saw earlier, was delta square. So k square x square would be in fact delta times x. I hope this part is clear. I hope this exercise makes sense to you. If you have any doubts, please stop me and ask me any questions. Sorry, this should be delta square x. So what we do here is we try to again bring it to the form that is asked here. In this case, they have taken out a delta by x term and written it as y by delta the whole cube and y by delta the whole square and y by delta the whole cube. So let's try to write it in that manner where we take out delta by x common, and since there is a power 1 delta here, we just have taken that out, but we have taken delta out in the numerator, so we have to multiply a delta in the denominator, and that would yield the 1 by 2 remains there, y square by delta square minus, from here what we do is we have taken a delta out from the numerator, so we multiplied with delta here giving delta cube. So the 1 by 3 remains, y cube is still there, delta square becomes delta cube, and the x has been taken out as common. Now we are very similar, we are getting an expression that is very similar to what was being asked, which is delta by x power 1 into 1 by 2 times y by delta square minus 1 by 3 times y by delta cube. This is the equation for the velocity, and from what is asked, that is exactly what we need, where a, b and c, a is the power of delta by x, b is the coefficient of y by delta the whole square, and c is the coefficient of y by delta the whole cube. So the power of delta by x is a equal to 1. The coefficient of y by delta the whole square is b equal to 1 by 2. And uh, the coefficient, one second, okay, there is minus c that's given here. So the coefficient of minus y by delta the whole cube is equal to 1 by 3. Therefore, yeah, therefore this is the answer. Where a is equal to 1, b is equal to 1 by 2, and c is equal to 1 by 3. Okay, if you have any questions, I'll just wait for a couple of minutes before I move on to the next question. Okay, so we'll move on to the next question. If you have any doubts, please let me know. So, in this question, it's said that a mercury manometer of density 13,550 is connected across the length of the pipe to measure the flow rate across the pipe as shown in figure 3. This is actually figure 3, not figure 1. Let the liquid flowing in the main pipe of density is equal to 2016 kilogram per meter cube and viscosity 3.57 Newton second per meter square, and is flowing at an average velocity of 7.3 meter per second. What is the nature of flow? This is a very direct, easy question. I am hoping you will all be able to answer it. So, what is the answer here? The nature of flow, whether it's laminar, or transition or turbulent, is given by the value of Reynolds number, which is the ratio of inertial to viscous forces given by rho times u times d by mu. Let's look at what all has been given. The liquid are flowing in the. So, which density should we take? Should we take the density of mercury or the density of the liquid that's being flowing? We should take the density of the liquid to be flowing, because that is the object of concentration, the object and the fluid under flow, and mercury is actually static here. So let's the diameter of the pipe is asked, the flow rate or the flow velocity of inside the pipe, and the viscosity of the fluid or the liquid is what's being asked here. So what is Reynolds number here? It's 2016 kilogram per meter cube times 7.3 meter per second times 9 centimeter is 0.09 meters divided by the velocity 7.3 meter per second. Just sorry about that. Okay, sorry about that. Let's get back to the question. So it's what is the value of Reynolds number? It's we'll get this as 371 point something. So what it means is that inside a circular pipe, we know that if it is less than 2000, we can call it as laminar, and if it is greater than let's say 4000, it's called as turbulent. Although this value is not exact, you can find this correct answer from the classes. Therefore, what is the most relevant answer here is that okay, sorry, a value of 371 would yield a laminar regime. Therefore, the answer is A, laminar. So I'll just wait for a couple of minutes. If you have any doubts, please let me know. Okay, so the next question: determine the flow rate or determine the volumetric flow rate through the pipe in meter cube per second. And this is also very straightforward, where volumetric flow rate Q is given by the velocity times the area, and the area is and the velocity is 7.3 meter per second times the area is pi by 4 times 0.09 squared. If you do this, you will get a value that can accurately represent this would be in meter square. So this value, let's actually do it together. So the flow rate would be just the velocity times area, which is 7.3 times pi by 4 times 0.09 square, which would be 0.046 meter cube per second. Okay, question number 7. The pressure drop across the manometer is. In order to calculate the pressure drop, what we do is just since it is in a laminar regime under a fully developed conditions, and it is flowing through a pipe, we can use something known as the Hagen-Poiseuille equation. And this is for Hagen-Poiseuille equation for finding the pressure drop in a pipe. Therefore, delta P, according to the Hagen-Poiseuille equation, the difference in the pressure is given by 32 nu times V times L by d square, and 32 times the viscosity is 3.57 times the length is given here as 2.5 meter divided by d square, as we said earlier, is 0.09 square, and we'll get a simple mathematical arithmetic solution here. If you solve it, you will get the pressure drop to be around in megapascal, it will be around 0.25 megapascal. And the question is asked in megapascal. And let's look at the final part of this question. The expected reading on the manometer, that is H reported in meters, is. So what we do is we just equate the pressure drop to the static pressure in on the manometric limb, which is given by rho gh, and here the mercury density has to be taken, since we are considering the static pressure that is associated with the mercury over here. Therefore, mercury density is 13,500 and actually it's 50 as given in the question here, times G is 9.81 times H should be equal to 0.25 into 10 raised to 6. And just by solution, we'll easily get the value of height to be around 1.93 meters, indicating that this height is roughly the height of a 6 foot 4-inch basketball player or someone similar to that. Again, these 4 questions are very fairly easy to solve. If you have any questions, I'll be happy to answer. I'll just wait for a couple of minutes so that everyone can, who needs to catch up, can catch up over here. Okay, so let's move on to question number 9, which deals with the Taylor-Quate flow. So it is said that we have in class it was the Taylor-Quate flow was discussed with an inner and outer radii of Ri and Rho, and the inner cylinder is rotating with an angular velocity omega I. We have to use this expression for the velocity profile and can calculate the contribution from the viscous stresses term in the theta momentum equation. So let's start by writing down what was the equation that we have derived in that was discussed in class uh, for uh, for the velocity, angular velocity omega I, or angular for the velocity profile that was obtained as u theta in terms of omega and r and ri, etc. The formula was omega I times ri into Rho by R minus R by Rho divided by Rho by Ri minus Ri by Rho. Now this is in the class. I think capital R and Ri and Rho were used, but effectively the meaning remains the same. So we know what is u theta. Now what we need to find out is to determine the viscous stresses in the theta momentum equation. So for that, let's write down the theta momentum equation, which is given by rho times dou u theta by dou t, that unsteady term, plus ur dou u theta by dou r plus u theta by r dou u theta by dou theta plus uz dou u theta by dou z plus ur u theta by r. Now this is just the inertial term, which is given, is balanced by the pressure term given by minus 1 by r dou p by dou theta, and the viscous term, which is mu times 1 by r dou by dou r of r dou u theta by dou r plus 1 by r square dou square u theta by dou theta square plus dou square u theta by dou z square plus 2 by r square dou u r by dou theta minus u theta by r square. This is the viscous term plus the gravity term in the theta direction. So let's just focus on the viscous term that is over here. The entire term is called as the viscous term, and let's find out what all directly goes to 0. We know that u theta is a function of r, and ur and uz are equal to 0. So let's, the first term will remain because u theta is a function of r. The second term will go to 0 because u theta is not a function of theta, and u theta is not a function of z. Therefore, the third term will go to 0. Again, dou ur by dou theta will go to 0 because ur is not a function of, there is no ur in the question at all. So there will be two terms that are remaining, which is given first by 1 by r dou by dou r of r dou u theta by dou r, and the second term given by minus u theta by r square as shown here. Let's take each of them separately, then combine them to further understand them. Let's take the first term, mu times 1 by, I'll just rewrite r in this way so it doesn't cause any confusion. Dou by dou r of r dou u theta by dou r. Therefore, you have to first find the differential of u theta with respect to r, and we know that u theta is given by omega times ri into rho by r minus r by rho divided by rho by ri minus ri by rho. So rho and ri are all constants. The only variable here is r. So the differential of the dou u theta by dou r would lead to omega times ri times differential of the quantity inside the bracket given by rho by r minus r by rho, and the denominator will effectively be unchanged because everything is constant. So I'll write that out outside the differential term. Now the differential of the terms inside the bracket can be performed. It's very basic calculation. And is given by differential of 1 by r is minus 1 by r square, and differential of r is 1. And this is just what goes over here. We need to multiply, this is just this is just dou u theta by dou r. So let's compute what is r into dou u theta by dou r. Now we'll just be multiplying this with r, and that will be given by minus rho by r plus r by rho. Sorry, this will again be minus. Now we need to differentiate this again, as we have multiplied with r, we have found out what this quantity is. Now we need to differentiate this with respect to r again. So dou by dou r of r dou u theta by dou r is equal to, let's just skip the first step and just write it down, ri by rho into dou by dou r of minus rho by r minus r by rho. And yeah, again I am writing down the entire expression for the first term, rho by ri minus ri by rho, and the differential of the second would be differential of 1 by r would be minus 1 by r square. So differential of minus 1 by r is plus 1 by r square, and the other term would be minus 1 by rho, since the differential of r is 1. Now this is just dou by dou r of r dou u theta by dou r. We need to multiply it with 1 by r and then with mu to get the final term here. Therefore, we'll get mu into 1 by r dou by dou r of r dou u theta by dou r should be equal to omega times ri by rho by ri minus ri by rho. And that will be equal to, just divided with an r over here, you get rho by r cube minus 1 by r times rho. So yeah, this is the first term in the equation for the viscous dissipation that's given here. Now let's calculate what is minus u theta by r square. And we know that u theta is again given by omega times ri by uh, rho by ri minus ri by rho times 1 by r square times r by, sorry, it's rho by r minus r by rho. Therefore, we'll get this as omega. Uh, there's a minus sign that's associated with the minus sign over here. You get minus omega ri by rho by ri minus ri by rho times, if we just simplify this, we'll get rho by r cube minus 1 by r rho, and this is minus u theta by r square. Therefore, the final expression would be the summation. Let me call this as equation 2 and this as equation 1. Therefore, finally it would be 1 plus 2. And what we see is that the coefficient term in both of them effectively remains the same, just a minus sign is there. And the term inside the bracket is exactly the same. It is rho by r cube minus 1 by r naught, indicating that these two terms when added will get equal to 0. Therefore, the entire exercise we have done is just to prove that the viscous dissipation term for such a case will be in fact 0. Okay, let me know if you have any questions. We have done some intense mathematical calculations over here. I just wait for a few minutes, giving you some time to catch up. If you have any doubts, please let me know. Okay, so let's move to the next question if you have no more doubts. Now it is given that this is a question on falling ball viscometer, which is given here. A small ball of diameter d, density rho v, when falls through a tube of test liquid of density rho and mu, density rho and viscosity mu, it attains a fall velocity. This fall velocity can be calculated by the time to fall a measured distance. The formula for calculating the viscosity of the fluid is given as this one. This is the something known as the free settling velocity or the terminal settling velocity. And there's also the term called as terminal settling velocity. This principle can be used to measure the viscosity of a fluid, and the instrument is known as falling ball viscometer. This result is limited by the requirement that the Reynolds number must be less than 1. Suppose a steel ball of specific gravity 4.9, diameter 2 millimeter, falls in SAE 25W oil of specific gravity 0.9 at 20 degrees Celsius. The ball travels at a distance of 195 centimeter in 1 minute. So we have all the details that we need to perform the calculation. We have our rho B, we have our rho, we have the viscosity mu. No, we need to find out what the viscosity is. We have the distance traveled and the time taken for the distance to travel, and we have the diameter as well. Therefore, we can just directly plug all the values into the equation for finding out the viscosity, which is given by g d square rho b minus rho by 18 into, I'm just rewriting this velocity as the distance traveled for the time taken. And substituting the values, I'll get 9.81 meter per second square times the diameter is 2 millimeter, which is 0.002 millimeter square, gd square times rho b minus rho, which is 4590 minus 900 kilogram per meter cube, divided by uh, 18 times. This ball travels a distance of 1.95 meters, which is 195 centimeter, in 1 minute, which is 60 seconds. Therefore, if I just perform a simple calculation, I can just directly get the value of the viscosity from here, and it will come out as 0.247 in the SI units, which is kilogram per meter second. Let's move on to the second part of the question. What is the Reynolds number? It is a very simple calculation, rho v d by mu, and the density of the ball is taken, the diameter of the ball is taken, the velocity of the ball is taken, but the fluid viscosity is the one being considered. Therefore, we'll get this as 4590 times the velocity is 1.95 by 60 times the diameter of the ball, which is 0.002, divided by the viscosity we just found out as 0.247. Here we'll get we can find out the Reynolds number from here. Therefore, we'll get the Reynolds number to be 1.2. Although in the answer in the question that was given in NPTEL, they have used the density of the fluid instead of the density of the ball, but that is the wrong calculation. We have to use the density of the ball instead of the fluid, and we'll get there is the Reynolds number small enough for such a valid estimate. We have just told in the question it is given that the Reynolds number must be less than 1. Therefore, the answer here is no. Okay, we have moved on to the practice problems, which is very similar to the ones that have been solved as the graded assignments. Consider flow of liquid density 890 and viscosity 0.3 through a 9 centimeter diameter pipe at an average velocity of 4.3 meter per second. A mercury manometer is connected across the length of the pipe. Determine the volumetric flow rate, which is Q, which is which is velocity times the area, which is 4.3 times pi by 4 into 0.09 square. And this I got it as 0.027 meter cube per second. The pressure drop across the manometer again can be found out to be the Hagen-Poiseuille equation. After we have verified that the Reynolds number is much less than 2000, which is the laminar flow. You can just directly substitute in this and you'll get 32 times 0.3 times velocity is 4.3 times the length is 2.5 by d square is 0.09. You will get this as 12.7 kilopascal. Again, please verify these answers as I also may make mistakes. Okay, now that we have done with week 3, let's move on to week 4, which deals with non-dimensionality and dimensional analysis and Buckingham pi theorem. So let's take a look at the first question. Laminar flow through a pipe is unstable at high Reynolds numbers. Investigations indicate that the Reynolds number for the transition to turbulence is approximately 2300 in a circular tube if the Reynolds number is calculated based on the diameter of the pipe. So let's consider a pipe and a flow through a pipe that's happening over here. If the velocity if the diameter is being considered as the characteristic length, then the Reynolds number has to be less or is 2300 implies that the flow is turbulent. If D is equal to 20 centimeter and the fluid is kerosene at 20 degrees Celsius, which has a dynamic viscosity of 2.7 to 10 raised to minus 6 meter square per second, find the volumetric flow rate that causes the transition. So first part of the question deals with finding the volumetric flow rate. There's no second part, there's only one part. So in order to find the volumetric flow rate, we need the velocity times the area. We know the area based on the diameter. We don't know what the velocity is. So for that, what we do is we know that the transition velocity is asked, so we consider it to be the Reynolds number to be the transition value, and we equate that and find out the velocity of the fluid. and we get that as 2300 times the viscosity is, oh sorry, so what is given here is mu by rho, which is denoted by nu, is 2.7 into 10 raised to minus 6 meters square per second, and this is the known as the dynamic viscosity. This is also known as momentum diffusivity. So therefore we'll get mu by rho as 2.7 into 10 raised to minus 6, and we'll have to divide this with the velocity, the diameter, which is 0.2, and we'll get the velocity as 0.009, oh sorry, 0.00975 meters per second. Therefore, what we need to find is the flow rate, and flow rate is given by velocity times area, which is pi by 4 d square. Therefore, this is 0.00975 times pi by 4 times the d square value is 0.2 square. Now this is in meter cube per second, but in the question it is asked in meter cube per hour. All we need to do is multiply it with 3600, and you will get the flow rate to be equal to 3.5 meter cube per hour. Okay, let's move on to the next question. Determine the dimension of the following combination of variables. Each symbol has the usual meaning. Let's first find out what the variables are, which is rho times dou u by dou t. You know that rho has kilogram per meter cube or mass per volume, or this length cube, times the velocity is length scale to length per time, and there is a differential of time here, therefore it is 1 by time. Therefore the dimension analysis of this would lead to m l raised to minus 2 t raised to minus 2. In option B, we'll get this as dou P by dou Z, and we know that pressure is force per area, and there is Z over here, and force is kilogram meter per second square divided by L square times L. So we'll get this as m L raised to minus 2 T raised to minus 2. Option C, we'll have to find out what is rho times Cp times dou T by dou T is. And we have just shown that m, the density is m by L raised to 3. Cp has a unit of joule per gram or joule per kilogram Kelvin. And we know that joules is force times the distance, which is kilogram meter per second square times meter per kilogram Kelvin. In the dimensional form, we can write this as m L T raised to minus 2 times L by m times Kelvin. And dou T by dou T would be equal to Kelvin per second. Therefore, the dimension analysis of this term would in fact be m L raised to minus 1 t raised to there's a t square. Yeah, okay, there's a t square t raised to minus 2. This is not in second, this is in t. That's what the mistake is. T raised to minus 3. And the fourth dimensional quantity was triple integral of rho dou u by dou t times dx dy dz. Now, what you need to understand is the integration or something does not matter, because what you're doing is just multiplying to find the area. So what we have to do is we have to find the dimensionality of this, and which you will get by writing down as m by L raised to 3 for density times L by T for velocity times 1 by T, which corresponds to the time over here, times length times length times length. Therefore, I'll get this as ml t raised to minus 2, which is very similar to the equation for force. Now, among the options that is given, which of the following matches? We see that A and B are matching, which is not matching with C and not matching with D. Therefore, in my analysis, I found the dimensional formula of A to be equal to dimensional formula of B, and C and D do not have the same answer. Therefore, option D would be, no, sorry, not D, it will be option G that would make the best sense. Again, please let me know if I made a mistake, because the answer that is given in the website, in the Swayam portal, may be different from what I got. Yeah, so I'll just wait for a minute, see if you are able to get these values, and then we'll move forward. Okay, so moving on to question number 3 in the week 4 questions. We have the first question as the convection heat transfer data are often reported as a heat transfer coefficient H, defined by Q is equal to HA delta T, where Q is in heat flow in joule per second, A is surface area in meter square, delta T is the temperature difference in Kelvin. The dimensionless form of H is called the Stanton number, which is very relevant in heat transfer problems. It's a combination of H, that is fluid density, rho, H, or fluid density rho, specific heat Cp, and the velocity V. So, starting from the hypothesis that Stanton number is H power A, rho power B, C, P power C, and V power D, which of the following is true? So we know that Stanton is a dimensionless number. Stanton number is represented by St, is a dimensionless number. So if you have to represent that in terms of H power A, rho power B, Cp power C, and velocity power D, we need to equate the dimensional formula of each of them to 0. Now, how do we find out what is the dimensional formula of H? That is why this equation has been given, where Q is equal to HA delta T. So it is given that Q is equal to HA delta T. We know that Q has a unit of joules per second, which is commonly referred to as watts. And H, we'll just keep it as H, and area will have a unit of, let's say in the SI unit, it will be meter square. Delta T will have a unit of Kelvin in the SI form. Therefore, H will have a unit of watts per meter square Kelvin in SI. If you write the dimensional formula, we'll get watts as joules per second. Joules is force times distance. Therefore, it will be mLT raised to minus 2 times the distance divided by seconds times the meter square, that is L square, times Kelvin. Therefore, if we just rewrite this, we'll get m T raised to minus 3K. So there is no length scale that is associated with the heat transfer coefficient. Now we'll just plug this back in to the equation for Stanton number, and then make sure that the powers are equated to 0. So we'll get Stanton number, which is m raised to 0, L raised to 0, T raised to 0, should be equal to m power a T power minus 3a K power a times density is kilogram per meter cube, which is ml raised to minus 3. Therefore, it becomes m power b L power minus 3b. Cp, as we have just did earlier, we'll get the Cp as this whole term, which is L square T raised to minus 2 K raised to minus 1. And it will be L square T raised to minus 2 K raised to minus 1. And if I substitute Cp raised to C, I'll get L raised to 2C, T raised to minus 2C, and K raised to minus C. And the velocity is written in Lt raised to minus 1. If you are raising it to the power d, we will be getting it as L raised to d, T raised to minus d. We just need to group them together in terms of m, L, T, and K. We'll get m raised to a plus b. We'll get L raised to minus 3b plus 2c plus d. We'll get t to the power of minus 3a minus 2c minus d. And finally we'll get k to the power of a minus c. So I think I made a small mistake. This should come out as k to the power of minus a. Yeah, this is minus 1. So k to the power of minus a minus c. And as I was saying earlier, we just have to equate this to m raised to 0, L raised to 0, T raised to 0, K raised to 0. There is also a k over here. So when we do this, we'll get 4 equations of a plus b is equal to 0, minus 3b plus 2c plus d should be equal to 0, 3a plus 2c plus d is equal to 0, and a plus c is equal to 0. So these 4 are the equations that we get when we try to solve them. Let's see which of them matches. The answer here would be option A, where all of them match. A plus b equal to 0, minus 3b plus 2c plus d equal to 0, 3a plus 2c plus d equal to 0, and a plus c equal to 0, as shown here. Okay, let's move on to question number 4. Derive the Stanton number if it is proportional to the heat transfer coefficient H. So what is given is if A is equal to 1, that means Stanton number, okay, let me just zoom in. Okay, the Stanton number is proportional to H. That means A is equal to 1 in the previous equation. So if you put A is equal to 1, we'll get A plus B is equal to 0. That means B is equal to minus 1. We get A plus C is equal to 0, which means C is equal to minus 1. And we know that minus 3A plus 2B plus, okay, let me just take a look at that, minus 3B plus 2C, sorry. Minus 3B plus 2C plus D should be equal to 0. We'll get 3 minus 2 plus D should be equal to 0, or D is equal to minus 1. Therefore, if you are writing Stanton number as h power 1, rho power minus 1, v power minus 1, and cp power minus 1, we will get h by rho v cp. Stanton number is given by h by rho v cp. So Stanton number is actually the ratio of the convection to the storage, energy that can be convected to energy that is being stored. So the correct answer again here would be option A, where Stanton number is given by h by rho v cp. Okay, let's move on to question number 5. The pressure drop per unit length is delta P by L in a porous rotating duct. Depends on the average velocity V, density rho, viscosity mu, duct height h, wall injection velocity Vw, and rotation rates omega. The dimension analysis gives the following expression for this problem, where f denotes a general function. All we have to do is we just all the options that are given are in the just check that they are in the non-dimensional form. So pi 4 will be a non-dimensional form. We just have to check with the others. So delta p by L h by rho v square will have the unit of so h is the height, so this will be in length. So when you do this, you'll find out that these two gets cancelled, this gets cancelled, and yeah, so these two get cancelled, these two get cancelled, yeah. You'll get m raised to 0, l raised to 0, t raised to 0. The next term will be rho vh by mu, which we know is similar to that of Reynolds number. Therefore, this will be m raised to 0, l raised to 0, t raised to 0. And the next number will be omega h by v. So omega will have a unit of time inverse, h will have a unit of length, velocity will have a unit of meter per second, or lt raised to minus 1. Therefore, again, this one will have a m raised to 0, l raised to 0, t raised to 0. And yeah, I guess that's all what we've asked. So what we need to understand is, if we can write pi 4, when we do the analysis, if you write pi 4 as a function of the other terms, that is delta p by L h by rho v square into r comma rho vh by mu and omega h by v, we can rewrite these equations as exchanging each of those terms. That means delta p by L into h by rho v square can be written as a function of pi 4 rho v h by mu and omega h by v. Similarly, rho v h by mu can be written as a function of this, this, and this, and omega h by v can be written as a function of these three terms. Therefore, that is how the question is being phrased. Which are the following dimensional analysis gives a correct expression? The answer would be all of the above. Basically, if you do the proper dimension analysis, you will get you will be arriving at this conjecture. Okay, let's look at the next question. A tank of length L filled with water up to a depth of h and depth h is made to oscillate. The surface of water will oscillate back and forth at a frequency omega, which is assumed to depend on the water density rho and gravity g. Rewrite these statements as a dimensional function. So what we can do is, what we need to do here is just to rewrite them as a dimensional function. So what we can do here is, we don't have to do that. We just have to write the answers for this part. How many non-dimensional numbers are involved when the description is analyzed? So there are five free terms, which is L, H, rho, omega, and G. There are three dimensional parameters, which is M, L, and T. There's no temperature over here, only time here. So therefore, the number of non-dimensional numbers or the pi variables will be equal to this 5 minus 3, which is 2. If we write this in non-dimensional format, we'll have to rewrite the expression for L, H, rho, omega, and G in the dimensional form, as H is L power 1, L is L power 1, rho is equal to M L raised to minus 3, omega is equal to T raised to minus 1, and G is equal to L T raised to minus 2. So what we can see is, if you are writing omega as a function of all of this is rho, L, H, and G, and I can rewrite this omega as rho power A, L power B, H power C, and G power D. So what we can do is, omega is given by T raised to minus 1, rho is M L raised to minus 3, I can write A over here, L raised to B, H is again length scale, so L raised to C. There's a difference between this L and this L. This L refers to the length, this L refers to the dimensional formula for distance L. And G is L T raised to minus 2, so it is L raised to D T raised to minus 2D. What we have now is actually an equation that looks like this. So the first equation, what we can find out is, we can write this as M L raised to minus 3A plus B plus C plus D, T raised to minus 2D is T raised to minus 1. From here we'll get D as equal to 1 by 2. We'll get A to be equal to 0. We'll get minus 3A plus B plus C plus D is equal to 0. Please just excuse me for just a second. Hello? Yeah. So you've just found out that a equal to 0 and minus 3a plus b plus c plus d is equal to 0. But what we need to understand is we are not able to identify, since a is equal to 0, we can just write as b plus c plus, or b plus c is equal to minus 1 by 2. But what we are not able to understand is which one is more crucial, whether it is L or whether it is the this dimension L, or it is L, or is it this H which is more important, is not able to be recognized. So if we write omega here, we'll get omega is equal to rho power 0, L power B, and H power C, and G power D. And D, we know that it is minus 1 by 2. But we are not able to distinguish between L and H. So the next question, when we do it, if the length of the container is double to twice the length 2L, the new sloshing frequency omega nu will be equal to how much? So since we are not able to distinguish between the length and height, we have to say that the answer cannot be determined here. Similarly, if the height of the container is double to 2h, the sloshing frequency b. It will give the same answer because we are unable to distinguish which one plays the more important part based just on the dimensional formula. That's why these dimensional formulas have a drawback that you don't know what you are exactly doing here beyond a certain point. You cannot finalize on anything. And the next question, if the fluid is in the container is replaced with a new fluid of density 2 rho, then the sloshing frequency will be what? We just saw that there is no dependence of sloshing frequency on the density. Therefore, even if the density of the fluid is doubled, or density of fluid in the container is doubled, the sloshing frequency will effectively be the same. And the last question for the solved problems is, if a tank of water sloshes at 2 Hz on Earth, how fast would it oscillate on Mars, where G is 3.7 meter per second square? This is found out just by taking the equation where omega is, where omega is proportional to G raised to minus 1 by 2. Therefore, omega on Earth by omega on, where is it, Mars? Yes, is equal to the gravity on Earth by gravity on Mars to the power minus 1 by 2. And we can just find out what the omega Mars is equal to based on this. We'll get it as 2 times gravity on Mars is 3.7 by 9.81 power minus 1 by 2. Yeah, and the sloshing frequency will be 1.23 Hertz. I hope this makes sense because the weaker gravity makes it easier to oscillate on Mars. And these kind of questions will become, hopefully will become more relevant as we are planning a trip to Mars soon. So moving on to the practice problems, it is a very similar questions. So I don't think I have changed the questions from what is being given. Find the volumetric flow rate that causes the transition. It is again very similar to what we have already did. 2300 is equal to rho u d by mu. And only thing different is d is equal to 10 here, that's it, or d is equal to 0.1 meter here. The last part of it determine the dimension of each of the following variables. I've already discussed how to do this. Just let me know if you have any doubts here. So I'm not gonna do this question for now, and I guess we'll stop here and end the session for today. If you have any doubts, please feel free to contact me. If you have any questions, just feel free to come to the session. And yeah, that's it. Thank you.